Okay, so let us just have a refresh back from yesterday session. Okay, yeah. So this figure is the one that's very important. Um, this is where the operation the operation condition or the operational area for the sieve tray where um, where it uh, yeah this is the operation where you have a satisfactory operation. So we have to design the tray column so it doesn't have flooding, it doesn't have entrainment, and it doesn't have downcomer flooding, and also it doesn't have excessive sweeping. Okay, this one is very important, so I'm gonna um, maybe put a screenshot, yeah, there, so I can put it for the if I want to write something. The second one that we the important one is the schematic. This one. Let me make a sketch. Okay, and then I think I will use share desktop so I can check whether we have complete a blank presentation so I can write something, yeah. So this picture, and the second one is the okay. So I think I'm gonna go back yeah forth and back there because to discuss something here. Okay, now let's go back to the Excel file. Okay, so just to remember again from yesterday's discussion, uh, for the scheme of the tray, here we have uh, the plate above, and also we have the actual plate, and also we have the plate below. Let me put it here so I can draw, yeah. Okay, right. So okay, here, yeah. These sides is called downcomer. Okay, so this area is called the downcomer, and here the height of the like some sort of a baffle, ya, kayak tanggul, ya, tanggul kecil to hold the liquid flow is called weir. Okay, there, and this is the active area. Okay, so if we have too much liquid, if we have too much liquid and then the liquid is kind of dripping inside jatuh ke bawah or dripping, it's called weeping. So in this area, it's called weeping if we have too much liquid. Yeah, so the liquid will dropping there. Yeah, like in you have a liquid on the steamer, and then just the liquid will just drop. Okay, but however, if it is if the vapor is too high, what happens is the vapor can push the liquid over here to the above plate. Okay, and that they will resulted in entrainment or carryover. Okay, so if we go back to here, the entrainment, yeah, that happens when the V is much higher than the liquid. So they just took all the droplets, all the spray onto the to the top tray. So then it will have excessive entrainment. So of course we don't want that one. Okay, then if we have quite a lot liquid but also high vapor rate, what happen is not only entrainment here, but it's called entrainment flooding. Flooding. Okay, so if you think about it, you have flooding, banjir, yeah, but it is on the entrainment or in the carryover. Okay, but if you have a high vapor and also high liquid rate, what happen? You have a downcomer flooding. So what does it mean with downcomer flooding? This one is actually the liquid is too high, so before even it is contact with the vapor, it will go to that one. Yeah, so it's called downcomer flooding. Okay, maybe you need time to familiarize all those terms, but that's fine. We can go back to these two important pictures, and then to check again what does it mean with all those criteria. Okay, right. So now I'm gonna go back to the third column design. Okay, so in tri-column design, we have the liquid and also the vapor, and then ideally all the liquid will contact with the vapor, and then so the new liquid will go out with the new composition, and the vapor also will have a new composition based on the equilibrium. Okay, it's not really good here. Okay, so there are the flow of the pattern. There's a froth regime, and also there is a spray regime. Yeah, so I think it has been explained in the previous one. In the froth regime, you have bubbles or vapor surrounded by the liquid, while in the spray region you have a droplet of a liquid surrounded with gas or vapor. Okay, and this also a picture about the whole area. There are sorry, this is a little bit black and based on the scanner, yeah, but actually there are two types of the whole arrangement. there are for sieve tray, of course, there are triangle, and there is a square like this. Looks like maybe similar with the heat transfer, yeah. Okay, and the top tray feed and the reflux inlet, there are a number of types, yeah. Yeah, all the schematic, number of types. And then this also what happen if we have intermediate feed, or we have multiple feed, or we have the apa ya, the side stream. We actually can try to check it's some for example like this. So you have the liquid, for example, in here, and then the liquid before it goes to the next tray, it can be tapped here. It can go out in this side. Okay, yeah, that's some of the intermediate ranges feed. Oops. It's not really clear, so I think I'm gonna just skip it, because I think we don't need this one as well for this single tray. Okay, and also what happened in the reboiler, yeah. In the reboiler, the lower stage is this one, yeah. Why? Because this is actually the reboiler return as the bottom feed there, and then this vapor will contact with the liquid from the top, and then that they will have one equilibrium stage. Okay, this is also practice to be avoided in the top bottom feed arrangement. Just gonna skip this one. A type of reboiler, just a lot of I think this one there. Okay, and this is also the type of downcomer. There are a vertical apron, there's all incline apron, there are inlet wear, so in the wear there is an inlet as well. And then for the plate contactor, I think we have discussed this graph before, so I'll just gonna skip it before we go to the algorithm. Okay, and the liquid flow pattern also in the previous description, and also the stability diagram, yeah, about whipping and so on. Okay. Okay, so right. Okay, now let's start seeing what happened, and then how to design the tray column. Wait, what happened? Stop! Wait. Why it just jalan sendiri ya? Give me 1 second, yeah? Or 1 minute. What happened? I think I need to close it. I'm gonna close the file and reopen. Okay, good. Okay, so when we want to uh, when we want to design the tray column, the first one that we have to do is to estimate the diameter. How to estimate the diameter is actually based on the upper limit of vapor velocity. So um, uh, by checking the flooding condition on the vapor velocity, we can check how much is the uh, vapor uh, vapor flow, and then the vapor velocity is actually around 70 to 85 flooding velocity. Okay, and then the vapor velocity is actually the volumetric rate divided by the area. So uh, once we know the volumetric rate, of course we know the volumetric rate from the problem statement. Yeah, in the problem statement you have the mass flow of the vapor, the mass flow of the liquid. Okay, and from the mass flow of the vapor you can find the density of the flow, um, of those stream. Okay, and then with that you can find the volumetric flow rate. Okay, so if for example if we want to design the top column, find the flow rate of the vapor, and then find the density, and then you get the volumetric flow rate. So this is can be calculated. Okay, and then we also need to check how much the vapor velocity that we required, or it can be it is complied. Yeah, and then with that we can get the area by dividing volumetric flow rate with the vapor velocity. Okay, so then we can get the area. Now, so what is the area that we're looking at? Here we have the column area, which is a cross section of the tray column, and then we also have the downcomer area. Okay, we also have the downcomer area, and in this downcomer area, the liquid just falling to the lower tray, so it can't be counted, tidak bisa dihitung. It can't be counted as the active area. Okay, so and from the top there also another where, or there's also another downcomer area, yeah, from the top. So in essence that the active area actually the one that in the middle here. Okay, the one that in the middle here is the active area. And also don't forget, because in the tray there are a lot of holes, and we can also calculate the hole area as HAH. Oops. Okay, now the next one is how to estimate flooding velocity, or UF. It is based on the net area. So we have a vapor, and also the liquid, and also the diameter. Yeah. How to get the flooding velocity is there are a formula to get the flooding velocity UF. It's actually equal to K1. K1 is a constant, square root of rho L divided by rho V divided by rho V minus rho V divided by rho V, or actually the density of liquid minus density of the vapor, and the result is should be divided again by the density of the vapor. Okay, so the some of the restriction here, so the hole size should be less than 6.5 millimeters. The wear height, yeah, the wear height, the height of the tanggul, yeah, should be less than 15% of plate spacing. It should also apply to non-foaming system, and the whole area divided by active area should be greater than 0.10, and the liquid surface tension is around 0.02 Newton per meter. So how to get the K1? Now the question is how to get K1. The K1 is obtained from of a diagram with relation with FLV versus a K1. So FLV is a vector between that correlates a liquid and vapor, and it is actually based on the LW divided by VW, and then square root of rho V and rho L. Okay, so here uh, okay, so here is there is a graph. I think you can get it in the a book. Yeah, should be much better. So let's open the C notebook. There, you may want to have a look. Okay, it's quite a while. Okay, later. Sorry. Okay, so but it's actually this is a graph. So maybe you want to find the flooding velocity in the sieve plates. Let's check if we control S flooding velocity. Oh, quite long time. Okay then. Okay, so you in the book you will find a correlation between the flooding velocity here, the sieve plates, and also the K1. Okay, the K1, and it is actually based on the plate spacing. So this one is it's not really clear. Yeah, I'm sorry. I need to check with the real graph so you doesn't confuse with the graph. Let's have a look there. Packing. This my PDF looks like a very long one. Yeah. Okay, looks like I need to maybe install another PDF things. Yeah. Anyway, okay, let's just go back to here then. Oops. Okay, I think it's fixed now. There's something wrong with my PDF. Give me 1 second. I need to restart the PDF again. Sorry for the inconvenience. There's still something wrong. I think it's better if so I will use another segment using Pak Danu segment, yeah, the PPT. Then I think it's much better rather than we use the PDF. Okay, right where we are. This one. I think this one's better. Okay, now so first, yeah, so first we check again the tray area. Again there is the AC is the column area, okay, and then the AD is the downcomer, and N is the A net, while the A is the active area. So this is actually the one that we're looking at. Okay, and AH is the whole area, total semua lubang, and you can actually choose how much is your total whole area. Is it 20%, 8%, or 6% of the AA? Okay, of the active area. So sometimes you can choose. Okay, the next one is the where. Okay, so what is the where? You will know that there is a LW or the where, yeah. So this is the where, like tanggul, yeah, panjang tanggul is called LW. While the height, tinggi where, the height of the where is called HW. Later on, you will need all these parameters to design the tray column. Okay, and the height of the wear is actually it can be represented by 3 centimeters, or by 4 centimeters, or by 5 centimeters. Okay, so there are diameter, and there's the size of the wear. The third one is the tray spacing. Yeah, so the tray spacing, jarak antar tray, is actually designed with of course with some numbers here. There's 0.15, 0.25, 0.3, 0.45, 0.6, or 0.9 meters. This also you can choose. Yeah, so that's why the process is actually gonna be iterative. Okay, and if you look at the height of the liquid in the tray and also in the downcomer, we can define this as the height of the downcomer here. The liquid in the downcomer is called HB. Okay, the height, little bit of the the space over here is called HAP. Okay, and this is the height of the wear, and then this one is the height of the liquid over wear. Okay, and then between the two tray is called the tray spacing, or IT. Okay, so if you are a little bit of confused, or you need some time to digest it, that's fine. You can have a look and then check the this one here, tinggi cairan, yeah, that one there. Okay, so again, so the definition that we have to check first is the area definition, and also the where, tinggi tanggul, yeah, or also panjang tanggul, the length of the where. The third one is the tray spacing and the tray, and also downcomer, and also and again some of the parameters here. This is called HB around here, because usually it's always higher than the over here. And then the HAP, HW, and HRW. Okay, so then we also we can calculate the column area, for example, how many meters, the downcomer area, how many meters, the net area, how many meters, active area, and also whole area. It is for professional design or hasil sementara. Okay, let's check with the next slide then. Okay, now the most important one is how to estimate the diameter of the tray column. Okay, to first in the tray column we have to find the FLV. FLV, the one that I explained it before. FLV is a factor, and then you have the the formula, yeah. FLV is this one, yeah. FLV is W divided by VW, square root of rho V and rho L. So then uh, you have to find um, the the density of the vapor, density of the liquid, the uh, flow of the liquid, and also the flow of the vapor. Okay, I think this one is much better, so we have a better figure here. um, so this is a correlation between K1 and also FLV, and here you can choose how much tray spacing, but look at the book. There are some rule of thumb. There are some rule of thumb around 45 to 60. I think we need to check it. So this should be maybe around this area between 45 and also 60 between the tray spacing. So for example, you have the FLV 0.1. So what you do is to
Bu, sorry
yeah,
Bu, I think
yeah,
you're
yeah.
sharing the wrong presentation, Bu.
Okay, yeah.
You're sharing the PPT right now, Bu, the tabel area.
The table area, is it?
Yeah, right now. The module 6 segment 3.
Oh, really?
Yes, Bu.
Right. Uh, let's go back there. I'll put the desktop then. Mm, okay, this one. Sorry. Okay, yeah. So the first one, uh, so the algorithm to find the to find the tray, yeah, the tray dimension. First is we calculate the FLV, and then you find the LT or tray spacing. Okay, and then you find the K1 from the graph, and then check the correction for the K1, and then calculate the K1, the corrected one. Okay, I think I'm gonna jump into here, yeah, to calculate the diameter first. So first we have okay, before the diameter, we actually if we can check the number one, the previous one, from the description column. So okay, uh, you wow, that's still it's a little bit frustrating with this one. Okay, let's go back to the column description then. I think I need to uninstall uh, my PDF, yeah, Adobe, and then check it again. Okay, so just to remember again, so before we calculate the tray column diameter, yesterday I think we also have this. We need to uh, write again all the the flow condition in the vapor and also in the liquid, ya, cair dan uap. Okay, first you have the molar flow, yeah, LM, yeah, the molar flow, okay, and also you have the temperature, you know the molecular average um, in that area, yeah, in that tray, for example in the first tray for the liquid and also for the vapor, and with that you can also calculate the mass density, and then you also can calculate the mass flow, all LW and also VW, and then you also have the volumetric flow, yeah, and then you also can check in the literature how much is your surface tension of your liquid, okay, and we make this for top side and also from the bottom, bentuk bagian atas dan bagian bawah, okay. So because we know this, so once we know all of this value, so the next step is to go to here using the mass flow of the liquid divided by mass flow of the flow rate, and then square root of rho v and also rho l. Okay, those, and then you can calculate how much of liquid flow factor FOV around here, for example 0.1 there, and then you determine the trace spacing, for example the trace spacing is 0.45, then you can have the point there and then you read it there, and then you can read how much is your K1, okay, there. Your K1 is only if only applicable for the surface tension of 0.02. So if you have a liquid that doesn't have surface tension of 0.02, then you need to make a factor. The corrected one is actually K1, yeah, the number of K1 over here, multiply with surface tension divided by 0.02 order of 0.2, and then you will have the K corrected. Okay, so once you have the K corrected, then you can put it into the equation to determine the vapor velocity of the flooding velocity of the vapor, which is K1 corrected square root of sigma L, rho L minus rho V divided by rho V. So this is the U of the flooding. Once you got the U for the flooding, you can choose between 70 to 85% of the flooding to check as your vapor velocity. Okay, I'm gonna back here. Okay, so back to here. Because once we calculate the vapor correction, then you can get the flooding velocity UF. Then you can find the percentage of flooding. Yeah, you can find check the percentage of flooding, and then check the maximum vapor of UV. And then the next one, so we have to find the velocity. Velocity was okay. The next time, if we the next step is we have to determine the area. Okay, so the area is actually based on the downcomer area by the net area, the column area, the active area, the whole, and then use this table, and then after that we can find the diameter column. Sorry, which one? Okay, yeah, that one there. Okay, so so once you have the active area minus the whole area, you can get the area. So the area here, so here you have the you can calculate the diameter column. The diameter column is actually the based on the area, yeah, the column area, yeah, column area divided by phi, yeah, per 4. So you know the once you know the net area, the column area, you can calculate the diameter as well. Okay, so we can calculate the diameter. So, and then we can also check the whole diameter, and also we have to determine the height of the wire. Okay. So then it will result in professional design or design sementara. Okay. So after this, we need to check our design. So our design that we have the diameter. Oops. We have the diameter. We have the maybe the hole or the wear or the tray spacing, uh, and so on. Yeah, so we have those professional design, but the thing is, we haven't checked with some of the checking if the design is comply with no flooding, for example, if there is no entrainment or there is no weeping and so on. So after this, our professional design must be checked in order to fit all those criteria. Okay, so hasil rancangan sementara yang termodifikasi perlu dinamik sehingga untuk melihat kestabilan operasi. So the next steps is we have to put it into the testing to check the operation stability. Okay, so this one is the diameter of the column. Yeah, we know it already. And also the next one is so first, once we know the maximum of flow rate, yeah, and we know the maximum of flow rate, multiply with the flooding, and then here we also calculate the maximum of volumetric of flow rate based on the V MR and then rho multiply with 3600 with also the volumetric flow rate we calculate of the flow, and then we can calculate how much the net area, yeah, the net area which is QV divided by U. So the volumetric flow rate that we have divided by the U that we determine. Okay, and once of that we can find the diameter of the column by first checking the area of the column first, and it's defined as the net area divided by 1 minus percent of downcomer. Okay, and after that we can calculate the diameter column AC multiply 4 divided by rho. Okay, so here so it's a quite long time, and sometimes in the oral exam that we ask is actually how to determine diameter column. So even the question is looks like maybe very short or something, yeah, but it's actually quite a long time, yeah, it's a quite a long way. Okay, right, and after that we also can find the liquid flow arrangement. So if, for example, if we want to find in the single path in this area here, we have to check the diameter column with the liquid flow rate or QL, and for the QL we calculated with the mass flow rate of the weight flow rate, yeah, mass flow rate of the liquid divided by the rho to get the Q, and then check the liquid flow rate. It should be around this area. Okay, so if, for example, your diameter is 0.6 and then your liquid flow rate is around here, is still in the cross flow on the single pass, then it will result in the single pass for the tricolor. Okay, right, I think I'm just gonna pause this here, and then maybe I would like to ask to you, or you can ask me if you don't have a question. If you don't have a question, I would like to ask you. Any questions? I think the best thing is to try while doing the assignments. Yeah, so you have an idea there. Okay. So I just want to get the feedback from you all. So I think who want to answer my questions. To determine the diameter of the column, what are the parameters that should we prepare? So what are the parameters that should we prepare? Or maybe from this one. So what are the parameters should we prepare to determine the column diameter? Okay, or do you want to uh, have a look for like uh, maybe 10 minutes or 20 minutes? How about that? Well, let me try to put this one to do next, yeah? Um, this is important because before I continue to the next part, it is important if to for us to understand the sequence, yeah, the sequence. I'll add this with maybe I'll add this with edit mode. Uh, this one, let's write a PPT from Bandung. Okay, let me give those two as well. So we have the first one. It's actually all similar, yeah. If you want to see the PDF or if you want to see the PPT, that's all fine. This is just to oops, why, what's this happening? No, it's not working. We there. You also can check the PDF in the tri-column design here, yeah, if you want. While I'm try to put the PPT from Pak Danu as well, so you have yeah, two different kinds, things which is actually quite similar, but I think if you want to have more structured or nicer picture, you can, oops, no, again it doesn't work then. And the last one. Okay, everyone's all done. So let me uh, let me ask you to have a look uh, all this PPT based on my explanation, and then try to check it by yourself, maybe around 15 minutes. Is that enough? Yeah. And after that I will try to confirm with you if you have understand, or if there's any question that you would like to ask, okay, before we continue to the next part. Okay, how about that? Is it good? Can you open EduNext?
Yes, we can, ma'am.
Okay, good then. Right, let me stop share and also post the recording, and then you're free to have a discussion, and then we'll continue again after 10 to 10, yeah, 10 10 minutes from then. Let's us resume the recording. uh, let's have the PPT again. Okay, so this is a typical question that I will ask during the oral exam. Who should I ask? Nadifa. Nadifa, what have you read so far? How to calculate the diameter column? What are the parameters that you need to provide first? Nadifa, are you there?
Yes,
Yes?
according to the algorithm, we have to first determine the FLV,
Yeah. So what is FLV?
liquid flow factor.
Okay. And then?
And then from there, we can determine the K1 constant.
Right, yeah, this one, yeah. So first you have to calculate, you have to list also the flow rate, yeah, the flow rate of the liquid, the flow rate of the vapor. You will get it from the calculation of the multi-component distillation. Okay, so we if you remember about last week's lecture, uh, you will have the how much B, D, yeah, the distillate, the bottom and the feed, and with those mass balance you can also construct how much liquid you have and also how much the vapor you have in the top side and also in the bottom side. Okay, and from that in the molar flow, and then you have to change it into the weight. Okay, so and then you will get this value, right? Okay. Okay, so after we find the FLV and then find the K1. Kevin, what is the next steps?
Find a correction for K1, Bu.
Okay, and then?
Then after that, you find the flowing velocity, the flooding velocity.
The flooding velocity ya, kecepatan saat banjir ya, the flooding velocity. So the flooding velocity is actually but we can't use those flooding velocity usually between 60% to 80% ya. Pak Danu always says that okay, if you just near the edge of a cliff ya, kalau kamu ada di pinggir jurang, uh, tentunya kamu nggak ingin berdiri di jurangnya ya, because it's got very prone to flooding. Okay, so we can't use this velocity for the vapor, but we should maybe about 60 to 80% of the flooding velocity there, yeah. So which we need to choose the percentage of the flooding. Okay, then you will get the maximum flow rate. So and then what's next, Kevin?
Next, you have to calculate the maximum flow rate, if I'm not mistaken, Bu.
Okay, so what is maximum flow rate?
That formula that that you're sharing, Bu.
This one. Okay, yeah. So then again we also need to find, because this is the volumetric flow rate of the vapor. Okay, the one that you have QV here is actually the volumetric still in the I think it's still in the molar, and then you have to multiply it with the average of the number of weight, and also divide by the rho, yeah, the density, and then multiply with 3600. What is this? I don't know, but yeah, but this is the formula. Then you get the volumetric flow rate. So the volumetric flow rate is actually the volume of the vapor, yeah, the rate of the vapor, but in the volumetric one, how many meter cubic. Okay, and then what's next, Dama?
Dama, it's me or Dama?
Dama.
All right. Could you repeat, because I was sending my,
Right.
I was talking before.
All right, that's fine. So then how to get so once you have the maximum flow rate, the velocity, you got the volumetric flow rate, and then what is your next step?
Finding the net area.
Okay, with this one, yeah. So I'm basically giving you the answer, yeah. So if you check also the unit, yeah. For example, the Q, or the volumetric flow rate, for example, meter cubic per hour, for example, yeah. And then also the velocity, for example, meter per hour, for example. So for example, this one meter cubic or meter cubic per second. What happened with this one? Yeah, or this one is meter per second. So if you divide those cubic meter and meter, then you will have meter cubic, or is the area. Yeah. So what is the area that we're talking about? The area we're talking about is actually AN. So what is AN, Dama? You can go back to the previous slides.
The AN.
Yeah, AN. What is AN?
AN is, the N is for net area, net area.
Net area, yeah. So the net area should be the active area. Oh yeah, the net area should be this this one, yeah. So the column area minus the downcomer area. Okay, so the column area divided by the downcomer area, then this is the net area. So the volumetric divided by the velocity would be the net area. Okay, so because it's still in the net area, we have to find the column area in order to get the diameter. Yeah, just a very simple V r square equal to the diameter of a column. Okay, that one there. Okay, then after that, so once you get the diameter column, then we have to check for our calculation in the, for example, in the assignments. Usually we have to use a single pass, and to use the single pass we have to check it with the liquid flow pattern. Okay, with the liquid flow pattern, if the weight liquid flow rate divided by the rho L is around this area, and then check with the diameter of the column. If it is lies between the cross flow or the single pass, then you're in the right range. If, for example, in your calculation you're getting in this area or in that area in the double pass, what you need to do is to you have to maybe change the liquid on also the vapor. Okay, sometimes we can change that one. Okay, so this will tell you this will tell you about the, oops, why I should put it here. Okay, this will tell you about how to get the column diameter once you know the property. This is 4. Okay, now the design that we have is called provisional plate design, or design sementara. Yeah, then what we have to do, the dynamic test atau uji dynamic rancangan. Yeah, the dynamic test for the tri-column design in order to ensure that we fall in the those region. Yeah, in order to be sure that we're satisfy the area of the operations. Okay, so from the flow rate, the excessive entrainment, the flooding, the downcomer, and also the dump, the excessive weeping. Okay, so there are I think around 6 tests or something, so let's have a look. Okay, the first test is there are 6. Ya. First, is there any weeping? Apakah terjadi weeping? Ya. The second one, is the pressure drop satisfy the operation? Ya, apakah memenuhi kriteria pressure dropnya? Ya, so this is the first one. The second one is the pressure drop. The third one about the height. Ya. The height of the liquid, tinggi cairan, and the froth on the downcomer, is it okay or not? Yeah, or is there any downcomer backup or not? Yeah, let me copy the picture here. That's why I need this picture really good here, because we need to, so it's better for me to explain it. Maybe I can make it smaller. Okay, or okay, it's very long. Okay. I think this one is nice. Okay. Oops. Yeah. Okay. So the dynamic. So I think it's better if I can explain a little bit. So if there is a whipping or not, the first one, the whipping is actually when we have the whipping point, yeah, or dripping, when we have low, if the vapor flow is too low, and then we have quite a lot of liquid flow rate. So we don't want the liquid to have a whipping, yeah, ke bawah, the liquid, we don't want that. And the second one is the pressure drop. Is it satisfy the operation? Is it comply with the requirement? The third one, tinggi cairan and float sesuai or downcomer backup. So the downcomer backup is when we have the downcomer, for example, that one there. Yeah, this is the wear, and then this is the type of the flow, for example, go that way. And then if the it's too much froth, yeah, ada froth, ada busa, and then it goes back to that way one. Okay, so this is the downcomer backup. And then if the froth and the downcomer is okay, sesuai, yeah. And then also the residence time, waktu tinggal, ya, apakah sesuai the residence time? Is it not too short, not too long, but just okay? So there's also criteria for this. And also, is there any liquid entrainment, which is when the liquid carry over to the top? Is there any liquid entrainment there? Okay, so there are 6 tests that we have to check. If, for example, our diameter didn't pass this dynamic test, then we have to do the iteration. Okay, how to do the iteration? Then we have to do the change, for example, the diameter, or change again the percentage of flooding. Yeah, remember, because we based on the v, the velocity of the vapor. If we, for example, change the percentage of flooding, and then it's gonna change the area, and then it's gonna change the area of the column, and then it's gonna change the diameter, right? So so it's gonna be quite a long journey and then long iteration for you. Okay, so let's have a look with the first step. The first step, so this is really like really algorithm. Yeah, you just need to follow it one by one. So first, let's check the turn down, and then check the LW minimum, or the weight liquid rate. Yeah, and then wait, I need to check with my, okay. Right. Okay. Right. Okay. Right. This one. So, and then we have to calculate the wear. Yeah, the length of the wear. The length of the wear. Sometimes there's 5. There are 6, 8, something like that. And then calculate the HOW minimum, and then also H plus OW minimum, calculate, and then check the graph. Okay, I think it's better if we use this formula. Yeah, there. Okay, I think this one. This is called the uji whipping, or the whipping test. Okay, so first we find the minimum liquid rate. Yeah, for example, percent turn down, go calculate with the LW. The percent turn down is actually the minimum operation that the minimum load of your operation, where you still can do the job, yeah, where you still can do the distillation operation. For example, the turn down is maybe 70%. At 70% capacity, you still or at 70% of LW, you still have can operate the operation. Okay. And after that, we can calculate the HOW, height over wear. Is actually, this is the calculation, which is 750 multiplied with LW divided by LW times the rho, yeah, and then order of 2/3. If you're curious where we get the formula, we actually all get formula from the book, yeah, from the book, from the Synod. Okay, so if you think you like to check the real book, you're very welcome to check the book. If you want to check with the PPT, also is fine. So we just put it into the PPT, but actually the real design is on based on the book. Okay, and then the next one is the K2. So again, there would be a weak point correlation, it's very old one here, where it shows about the height of HW, the wear height, and also wear over wear here, height over wear, and to get the K, the factor. Okay, to get the factors, and then you get the K vectors, and then you can calculate the minimum velocity of the vapor to check the to pass the hole, ya, untuk melewati lubang. Okay, so then you calculate the U of the hole, the minimum. Okay, here, and then you also check the UH of the minimum nyata, ya, penentuan kecepatan uap nyata, and then you check if your velocity, the real velocity minimum, is more than the velocity of your calculation. Okay, if it is still more than the UH minimum of the velocity of the hole, yeah, the passing the hole in the minimum here, based on those criteria, then you pass the whipping test, lolos uji whipping. But if not, then that means you maybe need to change the turn down ratio. Maybe you have to make it higher, yeah, I don't know, or low, maybe higher, yeah, just higher, and then to check that this is gonna be your percent turn down to get the pass the whipping test. Okay, and then the second one is the pressure drop. Here we have the office coefficients. Yeah, the office coefficient here, and then is actually based on the perforated area, of H divided by HP, yeah, the perforated area here. And once you have the perforated area, you have the correlation of and then this is also the plate thickness and the hole diameter, and then you have the office coefficients. For the to check the hilang tekan or the pressure drop, we have to find the maximum hole of the vapor that passing the hole. Okay, the maximum of the vapor passing the hole is actually multiplied with the this one, which max with the QV divided by H height. Okay, the next one is the okay. For the uji hilang tekan or the pressure drop, for the pressure drop, in order to make the that one there, the syarat lulus to pass, the total of height, the passing, it should be less than 150 millimeters of the liquid. Okay, and there's some formula here to find the pressure drop on the dry plate, hanya di plate-nya saja. and also the residual head, this one, and then it is combined with the height of the wear and also the height of overwear, plus the dry plate, yeah, this one, and also the or the residual, and then you get the total. If the total height is less than 150 millimeters of the liquid, then you can so then your uji hilang tekan or the pressure drop is actually passing. Okay. Right. And then the next one is the downcomer. The downcomer area is actually the LT and L and HW should be more than HB, or this is I think this one is the an example with some numbers. They tell you how to calculate the downcomer and then put the numbers there, and then check the syarat lulusnya, yeah. Let me check the downcomer, this one, yeah. So we have to check this one, head loss, check with the AP and AD, and then using the head loss on the downcomer. And then the last one is the waktu tinggal, yeah. This shows you some examples of downcomer test, but they put an example. I think this is based from previous groups, yeah. They put an example of the numbers, and then check the numbers, the downcomer, and then the test is actually should be more than half of LT plus HW should be more than HB, yeah, the bottom. Okay, and the last one is the residence time test. For the residence time test, you want to find the TR, which is the area of the D multiply with the HB multiply with rho L and divide by L max, okay. And here the residence time should be more than 3 seconds, okay. And the last one is the entrainment. You have to correlate your FLV with the percent flooding, yeah. And if your percent flooding is less than 0.1, then you pass, okay. So it should be between that one there, yeah. So the FLV within the percent flooding. So even for example, you have FLV 0.04, for example, so you should be up to, you can handle maybe up to 80%, yeah, 85% is fine. But if you for example go to the lower FLV, you can't go with the higher percent flood, okay. But if not, then it can remain prone to entrainment. Okay, after you done, so the thing is with all the tests, if you pass, if you need to pass all of the tests. So here, based on here, there are 6 tests. If you didn't pass one of the tests, then we have to change again the diameter of the column, yeah. If it pass, everything's passing, and then also the ratio of the diameter and the height is okay, then you can call it a day, and then you can, okay, so this is going to be my design. Right, okay, so this is the illustration of the top plate, for example. This is also using an example. This is the, for example, this is the wear length. They put the wear length, for example, and then they use the diameter. This is the diameter of the column, for example, and then there's also the active area. Yeah, to get the active area, there's some line how not much a hole in it, and also this one there's also space around this one, and then that shows you those plate layout. Okay, I think that one there. Yeah. Okay, we also can you can have a look on the this one. Let me check again. Hopefully I don't have. Okay, so let's have a look with an example. Okay, so for example, let's discuss an example in example 11. You can also have a look later to check about this. Yeah. So for example, they have example 11.2, and then they have a lot of I think they have the conclusion already. Yeah, all the stages, the bottom, and so on, and then they have the minimum feed rate is 70% of the maximum, and then they use a sieve plate. Okay, so the first we have to check also the your calculation for previous steps. Yeah, in multi-component distillation. In the multi-component distillation, you will find out how many number of stage, for example, the slope of bottom operating line, which is L dash and V dash, and the slope of operating line L over V, the top composition, the bottom composition. I think this an example show that the second one is the water, and also the reflux ratio. Yeah. And then the next one, we calculate the flow rate from the mass balance. From the mass balance, they calculate how many vapor rate in the molar rate. Yeah, look at here, still in the vapor rate and the in the molar rate, and then you also have the vapor below the feed and the liquid below the feed. All of them here is still in the molar, because when we do the calculation, we use the molar base. Okay, but for the distillation column operation, we have to calculate it in mass or in volume. Harus dalam bentuk massa atau volume. Yeah. So then what we need to do, we have to check the physical properties. Yeah, they calculate the physical properties from, for example, the pressures, check again also the surface tension, and then check an example. Yeah, and once they have those surface tension, they can start checking the column diameter. I think I have to click. Okay. Okay. Yeah. So in the column diameter, they have the okay. Enable scrolling. Stop the chlorine. Okay. What happened with this one? Yeah. Or maybe let's put it like that. I think this one's better. I'm sorry, to make it smaller. Okay, just to make sure that yeah, I think this should be better, so it doesn't scroll. Yeah, so then after that they need to find the column diameter. Yeah, like your friend said before, that's right, you have to check the column diameter. Check the column diameter from the FLV. We also calculate two between the bottom and also the top. Okay, and after that they make a correction for the surface tension and on the top and the bottom there, and then they determine, ya ini ditentukan, determine the design about 85% flooding at the maximum flow rate. For example, they calculate how much percent flooding, and then this is, and then now they multiply it with to change from the mass to volumetric flow rate, yeah, from the hour into meter per second, and then they got the volumetric flow rate. And then with that they calculate the net area even in the bottom and also the top. And you can see here is actually they have different areas. In the bottom they need 0.4, while in the top they only need 0.28. Okay, so if the difference is too much between the top and the bottom, you can have different you can have different diameter, because it matters, and sometimes there are distillation column that, for example, a little bit bigger in the bottom, or sometimes bigger in the top. Yeah, it's also fine. Right. Okay, and the next steps is they check first the downcomer area. The downcomer area they assume, for example, 20%, yeah. So 12% untuk downcomer, okay. And then with that they can get the cross section area of the column diameter, the column area, and then they can calculate the column diameter. And here we have okay, so here we have different column diameter. If the base is 0.77, and also the bottom, the top is 0.864. Okay, and there's but if the diameter is not much, yeah, here we have 0.77 and also 0.86. Only the difference is only 0.1 meter, hanya berbeda 0,1 meter, atau hanya berbeda 10 centimeter. Yeah, you can try imagine you have the base is 77 meters. And then the top is 0.64. yeah, not much different. If you have not much different, then you can use the same diameter above and below feet to reducing the perforated area for the plate above the feet. Okay, so then after that you can't have any diameter you want, so you have to want to check the nearest standard pipe size. Yeah, the nearest standard pipe size is for example in this case is BS 1600. They have outer diameter of 32 inch or 0.8 meters, yeah, 0,8 meter, and the inside diameter is 0.79. Okay, so because this is, I think, the nearest one with your calculated one, then you can check it. Yeah. Right. Okay. So then this is gonna be your professional plate design. Atau this rancangan plate sementara, ya. Then they made, okay, so okay, let's make the column diameter. The column diameter that we want is the inside column diameter, which is 0.79. Yeah, this one, the inside diameter. Yeah, this is the one that we calculated, that we use as the column diameter. Don't put the outside, okay, because yeah, we need the inside diameter to calculate the column diameter. And then from here you have the column area, and then you determine the downcomer area, the net area, the hole, and so on. And then all of this is just as the first trial. Okay, remember this is a first trial, so maybe there would be iteration, yeah, or change of the topics there. Okay, and here the second one, then we want to have the test. the check whipping, and then you can, I think it's almost a few minutes to 11, so we can check here about how they check the whipping test. They check the pressure drop. Yeah, it is get 188, sorry, 138, so less than 150 millimeters. And then after that, we have the downcomer liquid backup also. They calculated from here. It's still less than the plate spacing and wear height. Yeah, this okay, this one. Yeah, it's still okay. Yeah, it's still less than the plate spacing and wear height, so the tray spacing is acceptable. And then the next step is the check entrainment. Yeah, the check entrainment should be 0. So 0.018, yeah, those epsilon here, yeah, it's FC, yeah, or something, yeah, this one there, kappa or that there. Okay, so and then so because it is okay, so percent flooding also 76 below the design figure of 85, so this also checking. Okay, so then if looks like this is an example, so they have a good example, then if all of them satisfy those operation, then we can make a layout. Yeah, so this is an example of try layout, an example in that one there, with the perforated area, the calming zone, and so on. Okay, and then you can write the plate specification, for example, the how much is the wear, how much is the hole the hole size, yeah, the plate number, and so on, and then even the material, mild steel, and the thickness of the plate, yeah, and the plate pressure drop, and so on. Right? Okay, this is one of the sample. This is gonna be also your assignments. We need to wait with the regular classes as well, so I would suggest you to just wait for another information from the team teaching from me and Book Grace regarding the assignment for this one here. And on Thursday, I will continue with high-sis calculation, hopefully. Once you, while you do the manually, you can also do the tray spacing and try sizing using high-sis. All right. Any questions or comments at the moment? No? Okay. So if not, there would be a lot of things to digest. Yeah, I'll try my best to put the recording also to the YouTube, and then you can wait up until you get the assignments from the team teaching. Okay, everyone. I think that's all for today. Thank you very much.